So let's look at change in enthalpy, and enthalpy is the delta H of the reaction. And there are four ways to calculate delta H. We can calculate delta H by the average bond energies, which we learned about in our POGL. In honors chemistry, we learned about calorimetry and how to calculate our delta H from that calorimetry. Today, we're going to learn about enthalpies of formation, and in a different video, we'll learn about Hess's law. So before we move into enthalpies of formation, let's just do a quick review. And if we were to look at this graph, all right, we see the energy of the reactants and the energy of the products. The products minus the reactants gives us our delta H. And if our delta H is negative, which in this case it is, we get an exothermic reaction. So this graph is exothermic. And if our delta H is positive, then the reaction is endothermic. But one thing to keep in mind here is a negative delta H value is favorable. So reactions would prefer to have a negative delta H value if they were able to do so. So let's look at our standard enthalpy of formation. This is the amount of heat lost or gained when 1 mole of product is formed. And that's the key there. We have to do it by 1 mole. Our system is going to be at our standard state, which is going to be 25 degrees Celsius and 1 atmosphere. Because we have heat lost or gained per mole of product, we have to write a reaction so that only 1 mole of product is present. Reactants also must be written under their standard conditions because the system occurs at its standard state. So reactants must be under standard conditions. So here we have an example, delta H prime F. This prime tells us that we are under standard conditions, all right, 25 degrees Celsius and 1 atmosphere. And this F stands for formation. So let's look at this example. Notice in each equation above, we have 1 mole of product. So my reactants have been written so that I only have 1 mole of product. So let's look at this third example. We have 1 mole of product. There's only 1 oxygen. Now we know oxygen gas is diatomic, so I have to have a half a mole of oxygen in the reactant side. And it's okay to have half moles because our main thing is to make sure our products have only 1 mole. So when we look at this example, solid carbon plus oxygen gas, this is exothermic, and I know that because my delta H value is negative. Because a negative delta H value is favorable, what this means is the product carbon monoxide gas is more stable than the reactants that it was formed from. All right, so that's what we mean by favorable. Our products are more stable than the reactants. Let's look at the second example. This example is endothermic, and I know that because my delta H value is positive. Therefore, C2H2 is not as stable as the reactants that it was formed from. So the formation of C2H2 is going to have to depend on some other things. All right, this isn't going to naturally want to form C2H2 unless conditions are favorable in other ways, which we're going to talk about in this particular unit, all right? So we're going to look at some other things that may change our mind. And our final one, let's just do this, is CO more or less stable? Well, we'll notice here our delta H value has been provided. It is negative, so it is exothermic. Therefore, it is more stable. So here we have some common elements at standard states, and these are also provided for you on the reference tables I gave you, but I wanted to put them up here on a slide because I think it's really important to notice. Elements at standard state are, what are we noticing? They are all 0. Now, let's check out bromine. Bromine as a liquid has a delta H prime formation of 0. Bromine as a gas is not 0. So keep in mind, bromine is normally a liquid under standard conditions, and we talked about that when we did our honors chemistry. All right, and we learned about the size of atoms and bond strength and Coulombic attractions and all those things that make bromine a liquid. All right, so because bromine is a liquid under standard conditions, it is more stable as a liquid. Bromine would much rather be a liquid than a gas. So diatomic elements are only 0 when in their most stable state of matter. So you have to be careful and pay attention to the states of matter and reactions that are provided for you. All right. If it is an element under a standard state, it must also be in its most stable form or most stable state of matter. So we'll notice here common elements. We have carbon as a solid, our metals by themselves in solid form, all right, and then our diatomic elements. All right, so how are we going to calculate delta H using our delta H formation values? And the way to do this is it's going to be the sum times the number of moles of the delta H of formation of products minus the sum of the number of moles times delta H formation of reactants. So the overall delta H is dependent on the number of moles, and that is very important. So let's do an example. Let's calculate the delta H of the overall reaction for the following equations. So our equation, the delta H of the reaction, is our sum of the number of moles of the delta H products minus sum of the moles of the delta H reactants. And these are the formation values. So we're going to use our chart, our reference tables that you've been provided. All right, so when we set this up, what are our products? Our products are HCl, and our reactants are H2 gas and Cl2 gas. And our moles, we use the balanced equation, 1 mole of product, a half a mole of hydrogen, and a half a mole of chlorine. And now we know that diatomic elements in their standard state, which hydrogen and chlorine are both gases in their standard state, are 0. So the only value that we really have to look up is our product, HCl. So go look at your reference tables you are provided, and you'll see that the delta H of formation for hydrochloric acid is negative 92.3. And when we solve, we get negative 92.3 kilojoules per mole. And this is dependent on the mole, so it is kilojoules per mole. All right, I'd like for you to pause this video, and I'd like for you to try the second example. Okay, so to solve this example, our equation is the same. So our products are going to be this calcium carbonate, and that's a typo, that should be calcium carbonate. Our reactants are our calcium oxide and carbon dioxide, and you'll notice I've included the moles here for each one, and they are all 1 mole. So then we're going to look up our values. Calcium carbonate solid has a value of negative 1206.9. Now we have the sum of the reactants. So calcium oxide solid is negative 635.5, and carbon dioxide gas is negative 393.51. So this is in brackets. This is the sum of the reactants here. So make sure you do the brackets, order parentheses, or I'm sorry, order operations are very important when putting into your calculator, my friends. All right, and you end up with negative 177.89 kilojoules per mole. So let's write the equation for formation of ammonia gas and solve for its delta H of the reaction. So if we want 1 mole of product, ammonia is formed from N2 plus H2, so nitrogen and hydrogen gas. So how many moles of nitrogen do I need? I have 1 nitrogen, so I need a half a mole. And I have 3 hydrogens, so 1.5 times 2 is 3, so I need 1.5 moles of hydrogen. And then we can just set up our reaction, and we need to plug in our values. Now, when we plug in our values, nitrogen is a gas, hydrogen is a gas, so they are both 0. So really the only thing we need to look up is the value for ammonia gas, which we find to be negative 46.11. So the delta H of the reaction here is negative 46.11 kilojoules per mole. So when you look at this, you know that this reaction is exothermic because of this negative value. So a lot of these we can figure out by using the delta H of the formation.